Welcome everyone, this is Brock Hedegaard from the University of Minnesota Duluth. This video series is intended to introduce you to finite element analysis using ANSYS. If you're new to ANSYS, you can download a free version of the software off the ANSYS website. You can check out the products and services, see products for students, and that will take you to free student software for ANSYS Student. Now the most recent version is 2021 R1. I'll be doing these recordings on a prior release, 2020 R2. You can download either, they should be very similar. Once you have ANSYS downloaded and installed, you can open it up through the Workbench. So the primary tool that you use to get in, Workbench 2020 R2, that's the one we'll open up today. And we're here. The Workbench is our gateway to the variety of analysis systems in ANSYS. So you can see them over here on the left, the types of analysis that we'll do. For this first introduction, we're just going to start with a static structural because that's probably the most familiar to most of you. So we'll drag and drop a static structural out into the project schematic here. And that will create a static structural analysis object for us. And you'll notice we can define engineering data, geometry, model, and eventually we'll get down to results. So we'll start off with engineering data. That's where we define our material properties. So let's double click on engineering data. And we can see that it lists all the materials that have been defined and their properties are defined down here. Now, to start this off, it automatically populates this with structural steel. We're just going to leave it like that. In a future video, we'll talk about how to define new materials. So for now, that's good. Let's close out of that tab. Brings us back to the schematic here. The next thing that we'll want to do is check our geometry. So right now, we don't have any geometry. If you right-click on geometry, there's a couple options that we could talk about. You can import geometry if you're proficient in, say, for example, SolidWorks. You can build a model in SolidWorks and bring it in. Or you can draw your own geometry in ANSYS in a program called SpaceClaim. So let's use SpaceClaim. So I can create new SpaceClaim geometry, or if you just double click on geometry, that will open up SpaceClaim. SpaceClaim is the built-in modeling software for ANSYS. You can see here's our modeling space. The first thing that I'm going to want to do is select my units. So if we go to File, SpaceClaim Options, and make sure that my units are going to be, for this case, I want to use metric. So click on units down here. It's a good thing I checked. So right now my units are imperial and inches. Let's change that to metric. By default, that'll set it to millimeters. So I'll say okay. And now I'll be modeling in the metric system. So for this problem, I want to define a beam. It'll be 2 meters long. And so I want to first select my sketching plane. So down here, there's a sketch plane. I'll select the XY plane. So if you move your mouse around here, you can see it's going to select a different plane. I want to select this XY plane, and then I'll click Plan View right here so that I'm looking at Plan View. I'm just going to make a rectangular beam, again, 2 meters long. So I'll click here to make a rectangle. I'll click at the origin. And the blue number that's highlighted on the bottom, I can type that in. So I'm going to type 2000 for millimeters. And I'll hit Tab. So hitting Tab will then go to your other dimension that I can specify that. So I will say that this is 200 millimeters deep. I'll hit Tab again, and then Enter will then enter your beam in. And so that's going to be my beam section. If I click here on Return to 3D mode, that will exit sketch mode. And now I have a 3D shape. So right now it's just a plane. If you want to navigate around, you can use the middle mouse wheel. So if you click the middle mouse wheel and turn, that will rotate. So it's Control and the middle mouse wheel will move around. And then if you scroll the mouse wheel, that will zoom in and out. So again, right now I have just a plane. I want to give this some depth. So the pull command will be used to offset or extrude a face. So I'm going to select this face. I'm going to click on this arrow and I'm going to pull it out. And again, it has that number there highlighted in blue. So I pulled it out arbitrary 270 millimeters roughly. Let's say this beam is 100 millimeters thick. So I'll type in 100 and hit enter. And so there I've extruded it 100 millimeters, and I'll hit escape to escape out of the pull tool. And now I have my beam. Now the last thing that I want to do is I want to define a loading surface for this beam. So let's assume that this beam is loaded here at midspan with just a point load. Now you're not going to be able to do an exact point load, and that's usually a bad idea in finite element analysis anyway. So we're going to make a small patch right there at midspan. So how we do that is we can split a face. And so right here we'll split. So I went to the design tab, split, and you can click on the face that you'll split. And then if you run your mouse along that edge, you can see I could just split it at a certain distance from that end. So let's split this at 900 millimeters from that side. And then also I'll split this face at 900 millimeters. Well, it's going to measure from that side. So I'll do 200 millimeters here. So to change from one box to the other, I just hit tab and then enters my command. If you want to double check this, you can measure things. And so if you go to the measure tab up here, there's measure. I can measure this object right here, and it says it's 900 millimeters long. I can also measure this object over here, and it's also 900 millimeters. So I'm quite positive that I've centered that thing, and then my loading patch itself is going to be 200 millimeters long. All right, and that's it for our geometry. So when you're done with your geometry, you can just close out of SpaceClaim. You don't actually need to save it. You can, and it's fine saving it. You can use the same geometry for other models. If you do not save, it will still automatically export it to your ANSYS model. So I'm just going to close. And now we're back in the Workbench. You can see my geometry has been updated. It has the check mark there, so it's complete. And the model is ready to run. So this is where we'll actually do the analysis. So let's double click on model and open up ANSYS Mechanical. So you can see my geometry has already been automatically put in here from SpaceClaim. Let's talk a little bit about how that we do the navigation. Mouse controls are the same. So if I click my middle mouse wheel, I can rotate. Control and middle mouse wheel will pan, and then scrolling in and out on the middle mouse wheel will zoom. Over on the left here, we see our outline. That's where we're going to access most of the tools that we need, plus this context menu up here on top. Lastly, the details box over here, that's where we'll input a lot of the specifications for each of the commands that we run. So we'll need each of those three. If they're not visible, make sure that you find it. First thing that we're going to do is we're going to check our material properties. So I can see if I open up geometry, I have a solid object here. I have one part for this. So that normally if you have multiple parts, they'll all be listed here. And if I look down in the details box, it says I have a material assignment of structural steel. So that's automatically been done for me. If I open up my materials tab, I also have my structural steel material right here. Again, that was pre-assigned for me, so I didn't do any definitions for this, and I can't actually change any of the properties here. So our material is good. Next thing that we'll want to look at, if we just go down this list, is the mesh. So the mesh will discretize my beam into a set of elements over which I can solve my differential equation. That's effectively what the finite element method is doing. To set a mesh, I'll click on mesh here, and you'll notice the context menu will change. So if you're ever lost at what things do, there are multiple menus up here. But most of the controls for what you're currently on are going to be in this context menu right here. Let's make a mesh. The first thing I'm going to want to set is a sizing. So let's click sizing. It'll make a sizing object here, and I can set my details for that sizing in my details box. So first I need to say where the sizing applies. So the geometry is highlighted yellow. That means I need to specify this. Currently nothing is specified. So no selection, I'll click there. It lets me apply, but I don't have anything selected yet. So let's select the entire beam. Your selection tools are right up here. So I can select vertices or nodes, edges, faces, or body. For this, I want to select the entire body. So I'll click body, I'll click on my beam, and then I'll hit apply over here. So once it turns blue, then this sizing is going to be applied to that blue selection there. Next, I want to change my element size. Let's set the element size to 50 millimeters here. So I've just typed in a 50 millimeter element size. Lastly, there's some advanced behavior down here, whether or not it's soft or hard. Soft is treating my 50 millimeter size as really a suggestion, where hard is going to enforce that 50 millimeter size as best as it can. Let's just leave this as soft. We have a very nice section. It's rectangular, so it's not going to have any issues meshing this. But if you have more complex shapes, you may find some difference between soft and hard behavior. Let's now generate a mesh. So if I go up here, again, to my context menu, I'm going to hit generate. And it will take just a little bit. It'll tell you down here what it's doing. It's meshing. And here's my mesh. So it's not a super dense mesh, but it should be good enough for this problem. Now that we have a mesh, we'll define the static structural properties. So this includes boundary conditions and loading. So let's click on static structural. And again, my context menu will change. And you'll notice there's options for loading here. and also supports. So for my supports, let's do those first. I want to fix both ends of my beam. So I want to fix this side over here, and I also want to fix the opposite end. So I'll click on a fix support. It wants me to select a geometry, so I'll select this face over here and I'll apply. And then I'll create a second fix support. I'll rotate that around, again using the middle mouse wheel. I'll select that face and I'll hit apply again. And now I have both of my faces are fixed. So lastly, I want to define a load. I'll define that as a force. So I'll place a force and I'll select my loading patch right there in the middle on top. I'll hit apply. And now I can define my magnitude of my force. So you can define this using a vector. I'm going to use components here. That makes it a little bit simpler. So components, you can define an X, Y, and Z component to your force. Here I have just a Y component. So I'm going to be pushing down on this beam from above. And so I'll define a Y component. It's going to be negative because it's acting down. And let's say it's negative 20 kilonewtons. So that's negative 20000 newtons. And that should set it. So that's all we need for our beam definition. Once we're ready to go, you can hit solve. And it will solve your problem. And it shouldn't actually take very long, so this should be a pretty simple analysis for ANSYS to do. It'll take a minute or so to maybe build the model and solve the finite element method. And in fact, it's already done. So it doesn't look like it did anything, but it saved everything in my solution tab right here. So if you click on solution, once again, we can go up to the context menu here, and we can look at a variety of different results. So they're all there, it's just not plotting them. So let's say I want to look at a deformation. Let's just look at a total deformation. I'd also like a stress, so we'll get an equivalent von Mises stress. That's a type of stress invariant that can be useful for checking yielding and things. And then let's also look at a normal stress. And for the normal stress, I'm interested in my normal stress in the X direction. That's my typical normal stress that would develop under this beam bending situation. So when I have normal stress selected here, I can select which normal stress I'm looking at. So X, Y, or Z, I'll leave that as X. And that should be it. So to clear all these lightning bolts, hit solve again. It's not going to go through the entire solution, so don't worry. It's just going to update my deformation and stress. And here are my results. So let's click on the deformation. Deformation is given as the displacement at any given location. So this is the total displacement. So you can see at midspan of my beam, I have not even 1/10 of a millimeter. So this is a very small displacement here. For my equivalent stresses, I can see I have a concentration of stress here, and at the two ends, just what I would expect. Normal stress is probably going to be the most familiar to us. We'll see that we have a compressive stress here on top and a tensile stress here on bottom. I know those are compressive and tensile. Tensile is going to be positive in ANSYS, and then compressive is a negative stress. And opposite on the two fixed ends right there. Now, if you're interested in getting a specific value at a location, we can use the probe. It's a rather rough tool, but it can help you visualize your results, where I can click, for example, on a position in my beam and get the actual results there. So at this location, I see I have a -7. I can check over here for the units, that's megapascals. And I can rotate it around, and I can see it on the bottom face, I have a positive 6.8, again, megapascals for my stress. So that's it for an introduction to ANSYS. In future videos, I'll talk about other analysis systems and more complex problems. So please subscribe if you like what you see, and I'll see you next time.